Hello students, today we are going to talk about CSMA CA, that is Carrier Sense Multiple Access Collision Avoidance. So here we are going to talk about collision avoidance. Again, this is another random access protocol. So CSMA is also a random access protocol. So similar to CSMA CD, it's an augmentation to the existing CSMA technique. So it is also a CSMA technique. So that is, it will sense the media before transmitting, and instead of just detecting collision as we did in CSMA CD, here it's something like as though we can tell its prevention is better than cure. So rather than just detecting the collision, like thinking what to do after the collision has been detected, here we are trying to avoid the collision. So CSMA CA was basically invented for wireless networks, and so to avoid collision, so three strategies are used. So the three strategies are namely the interframe space, that is IFS, the contention window, and acknowledgement. Let us see them one by one. So the first strategy is interframe space. So to avoid collision, so that is CSMA CA, collision avoidance. So to avoid the collision, so we prevent or we differ from transmitting a frame even if the channel is found idle. So if the station finds out that the channel is idle, the station does not send immediately. So what does it do? It will wait for a period of time, and this period of time is called as the interframe space. So we will be seeing this in detail sooner. So even though the channel may appear idle, so we are already seen this before in CSMA or CSMA CD, that though if the channel may be idle, some distant station might have been transmitting a frame, and maybe we have not yet received the signal, or maybe the first bit, or we have not yet sensed, it has not yet reached the station. So to avoid this, okay, so the interframe space or the IFS, it will allow some time, okay, so that I can wait even if it is idle. So if at all a distant station is transmitting, I'll wait for this time called IFS, so that if at all a distant station is transmitting, I can wait and listen to the channel to sense if at all it is a distant station is transmitting a frame. So in one way, this IFS, the interference space, you can also use this time to prioritize stations or frame type. For example, if at all there are 2-3 stations waiting for transmitting, and it is waiting for this IFS, so it is a frame space or it's a time. So if different stations have different IFS, so I can have a strategy. Say the station which is assigned a shorter IFS can be given higher priority, or the one which is having a lesser or a smaller interframe space could be given higher priority. This is just an example. So we could do that. Okay, so after waiting then for this IFS, if the channel is still idle, we are not going to send, but we need to wait for another time, and that depends on something known as contention window. That is the second strategy in CSMA CA. So one strategy is interference space. So the next strategy is contention window. So now let us look into the concept of contention window. So basically, contention window is an amount of time divided into slots. So think that we have some time, and I'm dividing that time into various time slots. So you can see this diagram here. So think that here, if the channel is busy, I will use any of the persistence technique actually. So let us just assume now that we are continuously sensing. So even if it is busy, we are continuously sensing, and at this point of time it is idle. So as I told you in IFS, that is interframe space, so though the channel is found idle, it will wait for some IFS, and this IFS is random time, and it varies from station to station. So we will wait for this IFS. Even after IFS, we wait for this contention window. So as I said, in contention window, so this is that window. So this is that contention window. So this means I am dividing this contention window into some time slots. You can see this lines here, no? These are the time slots. So a station, after waiting IFS, it should choose a random number of slots. So I can choose, say, one station chooses two slots, one station chooses four slots, something like that. So the number of slots in the window, it will change actually according to binary exponential backoff. What is this binary exponential backoff? So so one time slot could be one could be two, then double. So 2, 4, 8, 16, so like that. So binary exponential means that. So binary exponential strategy is used. So the number of slots in the window changes according to the binary exponential backoff strategy. It's similar to something like your p persistent technique. So suppose I have waited for some slot of this contention window. Even after that, it doesn't mean that I will directly send. So so the station need to again sense the channel after each time slot. So suppose I waited now for one duration, one window slot, then I'll sense. Then if at all it is busy, we'll wait for another two time slots. Or if at all previously I had waited for two time slots, I'll wait for another slot of time. Okay. So however, if the station finds that the channel is busy, it does not restart the process from the first. So what it will do, it will just stop the timer and restart it when the channel is sensed as idle. So basically here we are giving priority to the station with the longest waiting time. So different stations are given different contention window slots. So based on whoever has waited for the longer time, the priority is given to that station with the longest waiting time. Anyway, we'll get a more clear picture when we see the flow chart of CSMA CA. So though we tell that it is collision avoidance, still there are chances, some slight chances are there that collision might have taken place. We cannot completely tell that there will be absolutely no collision. We are avoiding collision. It is much better than thinking of detecting collision. So we are at least trying to avoid the collision, but doesn't mean that we are completely, there may be no collision. We cannot tell like that. So next strategy is acknowledgement. So with all these precautions, there may be still a chance of collision. That is so because of collision the data might get destroyed, or sometimes it may be that the data might have got corrupted. So we need to wait for an acknowledgement. So usually we'll have a timeout. So this in something like similar to your stop and wait protocol. So a positive acknowledgement within the timeout. Okay, that will guarantee that the receiver has received the frame. So we have to use these three strategies, that is the interframe space, contention window, and the acknowledgement in CSMA CA. So now we are ready to look into the flowchart. So this is the flowchart of CSMA CA. So let's start. So if a station has a frame to send, so initially as usual, we will initialize k is equal to 0. And then we have to sense the carrier, means sense the media. Carrier means the media, we know that. So we are going to sense. How do we sense actually? By checking the energy. Okay. So this we have discussed in the previous class. So here we are going to sense the carrier, and if at all the carrier is is it free? So if it is free, if it is not free, it has to keep continuously sensing here, that you can see. This we also saw in the previous diagram, so in the contention window diagram. So it is a sense if the channel is not free. If it is free, if the condition is true, then we will wait for the IFS. What is IFS? The interframe space, which is different for different stations. So it will wait for some interframe space time. So after that, it will choose our R, random value of R. So this is your actually your contention window. So not just choosing the value of r, so that a value of r should be between 0 and 2 power k minus 1, and I will use the rth slot. And then we use something known as send an RTS. Now what is this RTS? We will speak a little detail in the next diagram, but RTS means request to send. So the station, that is a sender, will send a request to send signal to the receiver and wait for a clear to send signal. So it's like asking whether I send, and waiting for some time to receive an acknowledgement from the receiver telling that yes, you can send. So send an RTS, that is request to send, and when you send, you set a timer. Okay, once you set a timer, so I have to wait for something known as clear to send, and this is sent from the receiver. So I am the sender, I will send RTS, I'll wait for CTS from the receiver. So, and this CTS must be received at the sender before the timeout. Okay, so I should receive the CTS before the timeout. If I receive, then I'll again wait for IFS. If not, I'll increase k is equal to k plus 1, and again, the same mantra how we have already done in all the methods before in CSMA or CSMA CD. So that we'll do again. Anyway, coming back. So if at all, CTS is received before the timeout, we'll wait for IFS and then we will transmit the frame. And I have told you already 3 things we have to follow. What is it? One is IFS, that is interframe space, then this contention window, and then we have to wait for acknowledgement. So we can't simply keep waiting for acknowledgement. So what we should do? Of course, set a timer and then we'll wait for the acknowledgement. So, and that acknowledgement should reach before the timeout. So if everything till now, if everything is proper, if it is true, then the transmission is successful. So suppose before the timer is timeout, if at all acknowledgement is not received, then again follow the procedure. K is equal to k plus 1. If at all the value of k is less than k max, what is a k max? That limit usually 15. If it is less than, then wait for your exponential back of time, and then again do your repeat the process. If not, abort and wait for some, we'll follow that, we'll see that sometime later. But usually, if at all k is greater than k max, we'll abort and usually wait for a long time and then again start with k is equal to 0. So something, it's like that. Okay, so this is the flow chart of CSMA. So what do? We set k is equal to 0, find out if the channel is free, wait for IFS, wait for condension window time, send an RTS, set a timer, wait. So before the timeout, I should receive the CTS. If everything till now is proper, wait again for IFS, send the frame, set the timer for receiving an acknowledgement. So 3 strategies have been implemented here. So now we'll understand it a little more better by seeing what is this frame exchange timeline. So it is something continuation of what you have studied in that flow chart, and we'll give more clarity here. Okay. So before sending the frame, so the first step is, of course, before sending the frame, what we have to do? We have to sense the medium, that is carrier sensing. So how do? We do by checking the energy level, okay, at the carrier frequency. So basically we can use a persistence strategy. Okay, so sense the channel, you can do your 1 persistence or p persistence, whatever. So here we can use usually the 1 persistence technique, because we are doing a lot of things here. We are using IFS, we are using contention window, we are using acknowledgement and all that. So the channel uses a persistent strategy with back off until the channel is idle. The same what we have seen in the flowchart. So once the station is found idle, do we suddenly send? No, we will wait for something known as IFS. Here we wait for a period of time called as DCF IFS, or it is known as DIFS. So here actually DCF stands for distributed coordinate function. So it's just a time. So think that it is some time. So it's a function or it's a IFS. Okay, it's a type of IFS. So it will wait for IFS. even if the channel is idle. So it will wait for DFS, and then as we have seen in the flow chart, it will give that request to send. What is request to send? The RTS. So after receiving the RTS, which will receive the RTS now? The receiver. So what we did till now, this is at the transmitter side. So this is at the transmitter end. So let us go to the receiver end. So this is happening at the receiver or at the destination. Okay. After receiving the RTS, this receiver will wait for some again on interframe space, and here it is known as the short interframe space. We call it as SIFS. Okay. So the destination sends a control frame known as clear to send. So a transmitter will send which one? Request to send, that is RTS. So the receiver will tell if everything is fine, it will tell clear to send to the back to the source station. So this control frame actually, it indicates that the destination station is ready to receive the data. I hope this is clear. So the source station sent the data after waiting for, again the source has to wait. So source will wait first for DIFS. So then before send, after receiving the clear to send, again it will wait for SIFS. We will see this using a diagram. So then the destination station, it will wait for another time SIFS, then it will send an acknowledgement. So we are done with the interframe space, and of course meanwhile we will also be using the contention window. Then we have to think about acknowledgement, because acknowledgement is needed because the station does not have any means to check for the successful arrival of its data as the destination, because there is still a chance of collision. So this is, it will give a very clear picture of what we have told in the previous slide. So here you can see the station. So it will follow whatever we have done in the flow chart, that and all will be followed. So sensing, then yeah, here we are waiting for the interframe space. So here station A is about to transmit, so it will send the RTS. So RTS is a frame, it's a request to send, it's a signal, or you can tell it as a flag or whatever you want. So it's basically a frame or a signal. So A is the source and B is the destination. Okay, so again this is a time space diagram. So y-axis is the time, and the remaining space, this remaining thing is the space. Okay, or your x-axis, the full x-axis is the space here. So space time diagram. So A has sent the RTS. So B, what it will do? It will wait for a SIFS. What is SIFS? Short interframe space. And then if everything is fine, okay, don't think that simply it will send. So if everything is fine, it will send the CTS. And again, as I've told you previously, the transmitter will wait for another SIFS time, and then it will send the data. Also you can see here the B will send a CTS kind of thing in all direction. Okay, it will send to the left, to the right, everywhere. It will send in space. So we are drawing it slant Y because of the propagation delay. So here it is as though it is signaling. So CTS, if you can observe here carefully, it is signaling the source to send the data. But for all the other stations, so all the other stations, it can be C, D, E, F, there can be any stations here. For all this other station, it is using something known as network allocation vector. NAV stands for network allocation vector. So it's a vector or a time duration. It is as though telling all the other stations that, look, the A is going to use this space, or it's you going to use this media for transmitting, and no other stations should transmit. So it's a network allocation vector. So during this time, only in this space, only A and B can communicate, or A can transmit the data to B. So once the B has received the data, complete data, it will again wait for SIFS, that is short interframe space, and then it will send the acknowledgement. So it will send the acknowledgement in all the directions. So for A, it is to indicate that the transmission is successful, and for the rest to indicate that the channel or the media is free. That is the end of network allocation vector time. So to make it further clear. So when a station sends an RTS frame, so when I say RTS, that is request to send, I'm also telling that I have this much of data to send. So if at all I can send, I have to be given this much of time for data, so that no other station should be transmitting during that time. So it includes the duration of time that it needs to occupy the channel. So the station that is affected by this transmission, so basically during that time, we network allocation vector is created. So that is done to so that other stations must be idle. So to check the channel for idleness. So each time a station accesses the system and sends an RTS, so the other stations will be in the NAV, that is the network allocation vector time. So in other words, in simple words, so each station before sensing the media, it has to check if NAV is present or if it has expired. And if at all NAV is present, it will get expired only after the source destination communication is over. And over means an acknowledgement is sent from the receiver back to the source. So the CSMA CA was mainly, mostly used for wireless networks. So it's not very sophisticated enough to handle some of the wireless related issues yet, such as the hidden terminal or exposed terminal. So we will see that. So these issues, some of these hidden station problem and all, okay. So these are solved by augmenting the above protocol with something known as handshaking features. So we have to see something known as handshaking features, which is actually already present to some extent. So what is this handshaking? So this RTS CTS itself is your handshaking actually. So now you imagine that during RTS CTS there is a collision. So what happens if there is a collision during the time when RTS or CTS, during that handshaking? What is handshaking actually? It's like a, the source and destination, they are having a sort of understanding, asking each other whether the source can transmit the data to the receiver. Okay. So if two or more think that A is trying to send RTS to B, C is also trying to send RTS to B. So two or more stations are trying to send the RTS frame at the same time. So there is a chance that these control frames also may collide. But there is no mechanism here for detecting such collision. So here it's like a common sense. The how to detect whether there is a collision. Obviously, we have set a timer, right? So the sender assumes that if at all it has not received CTS, obviously that there means there is a collision. So during that time, what we have to do? The backup strategy is employed, and the sender will try to send again a RTS. So it is understood here. So even if collision can happen during handshaking, how it is detected? Of course, if RTS is collided, it will not receive CTS. So that's it about CSMA CA. So there's a concept known as hidden station problem, which actually it's better it's explained in the class. So anyway, so in this lecture, what did we study? We studied about CSMA CA, the three strategies used to avoid collision. So that is the interframe space, the contention window, and the acknowledgement. So we also saw the flow chart of for CSMA CA and how it is used. We also understood about two handshaking signals, that is the request to send and the clear to send. So request to send from the transmit sender and clear to send from the receiver. We also understood the DIFS and the SIFS, that is DCF interframe space and the short interframe space, and how network allocation vector is used. So we have seen that. Okay. And we have also seen that the CSMA CA was widely used in wireless transmission. So this is about CSMA CA. So thank you.